You know that feeling, right? You're watching TV and suddenly the picture freezes up, gets all blocky and pixelated. It's annoying, for sure. But what if I told you that glitch was a tiny symptom of a much, much bigger problem? Okay, so let's get right into it. Take a look at this cable. You've probably seen something like this before. Maybe a squirrel got hungry, maybe it's just been baking in the sun for years and started to crack. You'd think, okay, worst case scenario, my TV signal gets a little fuzzy. But what if that little bit of damage could actually interfere with an airplane flying thousands of feet above your house? I know, it sounds completely wild, like something out of a spy movie, but this is a totally real-world problem that has a pretty wild history. To really get how this is even possible, we need to talk about this invisible thing called cable signal leakage. And you gotta think of it like a two-way street. It goes both ways. And we call these two directions egress and ingress. So ingress is what you usually notice. It's like a pipe leaking in reverse. Outside radio noise gets into the cable through a crack and messes everything up. That's your frozen picture. But egress is the exact opposite, and it's where things get serious. That's when the powerful signals inside the cable leak out into the air. So while ingress is basically a headache for customer service, egress can be a real, legitimate threat to public safety. And this isn't some made-up what-if scenario. This is a lesson that the cable and aviation industries learned the hard way a long time ago. The alarm bells really started going off in the 70s. But things got real in 1976 near Harrisburg, Pennsylvania. Pilots were flying out of the airport, and suddenly their communications with air traffic control were just gone, totally wiped out by interference. I mean, we're not talking about a little static here. This was a major safety scare, and it forced the FCC to get involved, create brand new rules, and eventually start handing out some pretty hefty fines. And here's the kicker. When they investigated, they found that this massive field of interference wasn't coming from one giant break in the cable line. Nope. It was the combined effect of a bunch of tiny little leaks all over the network, some as small as a single open cable port in somebody's living room. All those little leaks added up and created this huge bubble of radio frequency energy. Because of this, the FCC set an incredibly strict limit. At any single spot, a cable is not allowed to leak more than 20 microvolts per meter, measured from about 10 feet away. And just to be clear, that is a tiny, tiny amount of energy. But here's what's so wild. Look how badly that limit can be broken. Back in 2001, the FCC found one single leak in a cable system down in Texas that was spewing out over 2,400 microvolts per meter. That's more than 120 times the legal limit from just one spot. And believe it or not, this isn't just some old problem from the history books. It's actually evolved. Today, these exact same signal leaks are causing major interference with our modern LTE cell phone networks. So yeah, a bad cable system can actually mess with the cell service you use every day, which has kicked off a whole new round of enforcement from the FCC. So you might be wondering, how on earth do you find these invisible little leaks when they could be anywhere along hundreds or even thousands of miles of cable? Well, it takes a constant, really high-tech hunt. It all starts with this big picture view called the Cumulative Leakage Index, or CLI. You can think of it like a report card. It's a formula that tells cable operators the overall leakiness of their entire system. It gives them a single score, a snapshot of the network's health, and its potential to cause trouble. But the real work, that happens out on the streets. It is a non-stop job. Technicians have to drive the entire network, 100% of it, every 3 months. Their trucks are decked out with special equipment that's constantly listening for specific signals. They're called pilot test tones. These are frequencies that the cable company puts on the line just so they can be detected if they leak out. When the gear picks one up, bang, it logs the GPS coordinates and drops a pin on a map for a repair crew to go find it and fix it. And this right here is what that hunt looks like. It's pretty brilliant, actually. Every single one of those colored dots is a confirmed leak, pinpointed exactly where it is. It takes this huge invisible problem and turns it into a clear, visual to-do list. Now, all this detection tech is amazing, but it does make you ask a pretty basic question. What's actually causing all these leaks to happen in the first place? And the answer is usually way more simple and, well, low-tech than you'd think. I mean, at the end of the day, it's just physical wear and tear. A connector gets a little loose, or it starts to rust. A construction crew accidentally nicks the line. And sometimes it's just the weather. The constant heating and cooling, day after day, can eventually create tiny cracks in the cable's middle shield. And here's a perfect example. See that corrosion on the connector? That right there is basically an open door. Any little imperfection in that metal shield is just an invitation for those radio frequency signals to come pouring out. And here's where it all connects. All of these problems, whether it's corrosion or cracks or a squirrel, they all have one thing in common. This is a fundamental built-in problem with coaxial cable technology itself. Because it works by sending radio frequencies down a copper wire, it's just naturally prone to leaking. But there's another kind of technology out there, one that's getting more and more common, that is completely 100% immune to this entire problem. And that, of course, is fiber optics. See, fiber doesn't use radio signals and copper wire. It sends data using pulses of light through perfectly pure strands of glass. That light is physically trapped inside the glass. It literally cannot leak out and fly through the air. So there's no RF signal, which means there's zero RF egress. The problem just doesn't exist. This is such a fundamental physical difference that even the regulators, people like FCC Commissioner Michael O'Reilly, have pointed out that as we upgrade our world to fiber, all these old rules about leakage and the dangers they prevent, well, they just become obsolete. They fade away. So as we keep replacing those old copper lines with these new, silent strands of glass, it's about way more than just getting faster internet. We're actually permanently solving a hidden, invisible danger. And that kind of leaves you with one last question to chew on. What other old-world problems are we fixing, maybe without even realizing it, every time we upgrade our infrastructure?